But one of the most interesting one of all is the isotopes of helium. Oh my, helium is such a wonderful element. So the physics of the isotopes of helium. Oh my, this is a great one. I have a lot of favorites, but here we go. Let's go look at what we're looking at. So all I'm just going to do this time is that I'm going to go. There's only 2 isotopes of helium. Here they are. There's only 2 isotopes. You can see that there's helium-4 and there's helium-3. So when you look at helium-4 versus 3, what's the big difference between these 3? Between these 2? Well, this guy is like this, and this guy is like that. So when we look at these things, you could see that this is 2 neutrons. This guy is 1 neutron. And of course, they each have to have 2 protons. So the question is, you could see that the big difference here is 1 neutron, right? 1 neutron. How big of a difference does the neutron make? Well, for starters here, when you're looking at this guy, you can collect helium-3. Why? It's stable. And what you find here is that helium-3, so remember, from now on, I'm going to write helium-3 like this, okay? Helium-3 is, has been studied extensively. Yeah, I mean, in low temperature physics labs. And what you find here is that one can create liquid helium. And liquid helium, what we know about liquid helium is that it's a very bizarre thing known as a quantum liquid. And so what's beautiful about liquid helium is that you could see quantum effects at the macroscopic scale. The vast majority of the time, you can only see quantum behavior only at the microscopic scale, not the macroscopic scale. So before I explain what a quantum fluid is or a quantum liquid, is that I need to bring you up to speed. And we need to talk about the phases of matter. So the phases of matter tell us the state of a substance. And you're all familiar with this. Like, for example, we could start off with the gas. So what gas will I think? Well, let's think about water vapor. If you cool water vapor, okay? So if you cool water vapor, what happens? You get a liquid. And what is that liquid called? It's called water. But if I continue to cool liquid water, I can create a solid. And that solid is, of course, ice. So water has other phases, but the phase that we're talking about here is that the phase is either a gas, a liquid, or a solid. And so what you're seeing here is that these processes called phase changes change the structure of matter. Okay, so it changes the structure of matter, and you get that. Now we want to apply this to helium-3. So what are the phase changes of helium-3? Right? What are the phase changes? Well, it turns out that it goes like this. You start with helium gas. And then what do? You don't just cool it, you supercool it. So you go through a process of supercooling. And then what you find here is that now you get liquid helium. Okay, so now I've gone from a gas to a liquid, but now there is another phase change. And this is because, again, you go through a process of supercooling. So these are at ultra low temperatures. And then something dramatic happens. You go from liquid helium, and if you continue to cool, not even that much, it turns into a super fluid. In other words, a quantum fluid. So we got to be careful here in my language here. So remember, this is a phase transition. That is very different let me find my mouse, very different from a liquid. It is not a regular liquid anymore. Okay, maybe I should say that, from a regular liquid. It is vastly different. By the way, just for the sake of completion here, helium will never, ever become a solid. It will never become a solid. So there's no such thing as solid helium. Okay, so what happens here? So what we want to do here is that, now I could start with the question to try to set it up here. So what's so neat about liquid helium? Remember, I really mean, when I say liquid helium, I really mean helium-3, liquid helium-3. So here we go. So what we'll do here is that we're going to do the following thing. The first thing that we want to do is that, maybe I have a silly question, right? silly question. Suppose you're going to put water in a glass. Okay? You're going to put water in a glass. So you put water in the glass. I guess the question is, why? And of course, you're going to say, well, you have to put water into something so that you could transform it from one location into your mouth, I guess. But maybe the question that I'm really asking is this: why does the water stay in the glass? Why does water stay in the glass? Well, when I think about a water glass, what's really important? Right? I have a glass. And what I'm going to imagine here, of course, I don't have to imagine, we know that it's the case. There's thickness to the glass here, right? So the dark here represents the glass thickness, whereas in here is where it contains the water. So clearly the glass contains the water. So right in here, we're saying here is that the glass contains the water. No surprise. The question is, why does it not escape from the bottom? Right? That seems like a reasonable. And the answer is that atoms at the atomic level, what we find here is that at the atomic level, atoms appear to be empty. They appear to be empty, like empty vessels. So when you're looking at this thing, we could see here is that this is the bottom of the glass. And when I look at the bottom of the glass, I have what? I have atoms. So in other words, these guys here are my atoms, and they sort of have a lattice structure. So these guys here will be the glass atoms. But at the same time, I also know that I have water molecules. So when I look at water molecules, these guys are effectively devoid of matter. Doesn't mean that there's nothing there. And then these are water molecules. So what you find here is that what stops water molecules from going through glass is that we would say here is that in between I guess maybe not in between. How about I said slightly different? The water molecules experience an atomic friction from the glass molecules. That do not allow water molecules to escape. And this atomic friction is really about the electrical force between these guys. It's the electrical force that stops the molecules from leaving here. Now, let's get to liquid helium. Okay? So now I want to take this discussion towards liquid helium. What do I know about liquid helium? Liquid helium stops boiling at around 3 Kelvin degrees. So this is known as 3 Kelvin. 3 Kelvin, which is written roughly like this. This is, I don't know what it is in Fahrenheit, but I would think that it would be about 350 to negative 400 degrees Fahrenheit. So note that that's 400 degrees below zero. And that means is that when you get to these ultra cold environments, so this implies here is at ultra cold environments, helium-3 behaves like water. It's clear like water. You can pour it into glasses. No problem at all. And what you find here is that one can pour liquid helium-3 or can pour liquid helium-3 into a glass, like water in a glass. So now what I'm going to do is that I'm going to show you a video. It's a short video, but it's a powerful video. Okay. So here we go. Let's go look at this video here. I want to make sure that the volume's up. So this is part of a BBC show that's actually quite good here.
There were more surprises ahead. In the 1930s, another strange phenomenon was observed at even lower temperatures. This rapidly evaporating liquid helium cools until at 2 degrees above absolute zero, a dramatic transformation takes place.
Okay, here it is. Now the liquid helium, you saw it was bubbling, boiling, and now it acts like water. So I said 3 Kelvin, the video says 2 Kelvin, so I was off. Here we go.
Suddenly, you see that the bubbling stops and that the surface of the liquid helium is completely still. The temperature is actually being lowered even further now, but nothing particular is happening. Well, this is really one of the great phenomena in 20th century physics.
The liquid helium had turned into a superfluid, which displays some really odd properties.
Here I have a beaker with an unglazed ceramic bottom of ultrafine porosity.
Ordinarily, this container with tiny pores can hold liquid helium.
Okay, so here's where you want to look at this thing. You're going to see the phase transition right now. So right now, this liquid is contained within the glass bottom. Nothing is dripping out. When it goes through to a superfluid transition, you're going to see the liquid sort of like jump. Check it out.
But the moment the helium turns superfluid, it leaks through.
Can you see the drips at the bottom? It's going right through the glass.
We call this kind of flow a superflow.
Superfluid helium can do things we might have believed impossible. it appears to defy gravity. A thin film can climb walls and escape its container. This is because a superfluid has zero viscosity.
So let me go back to my my screen now, and let's talk about this thing here. So what just happened here? And let me try to explain what we're seeing here. So what you're seeing here is that, so I got to go back and correct it. It's not 3, it's 2. Okay, sorry about that. So it's at 2 Kelvin. So what you find here is that when you get below 2 Kelvin, you get to something called the lambda point. So what you're finding here is that at 2 Kelvin, the glass container can, I don't know, contain the liquid helium? The liquid helium. So that means here is that if I have my container, which I'm going to steal from up here, just to save time, I'm going to come here. And so what you're seeing in here is that down here, no helium leaks through the bottom. In other words, it acts like regular water in a glass. But then something strange happens. And so what happens here is that now what you see here is that there is a phase transition. Okay, so now what we're seeing here is that there's a phase transition to a super fluid. And what happens in the superfluid state is that now what you're seeing here is that the liquid helium is leaking out of the bottom here. So what you're finding here is that now you're seeing this thing go right through the bottom. So in this case, what we're seeing here is that the liquid helium goes right through the bottom. And what's really happening here is that, remember what we talked about before. So when we talked about before here, we had the layer of glass atoms. And then we had the layer, in this case, of helium. So now we have different atoms here, right? So here we had the glass atoms, right? So these guys are the glass atoms. And the helium, which I'll draw in purple this time, these are the helium atoms. So what you find here is that when it phases transition, it loses all viscosity. Viscosity means that in this case here is that there is no more atomic friction. So what happens here is that these helium atoms, they literally squeeze right in between the atoms, and they start to flow right through the bottom. That's what a superfluid is. It loses all its viscosity, but it gets stranger. And what they did here is that now they made a better glass. So they now made a better glass. And this is what they called a glazed glass. So the glazed glass can contain it now. So this means here, what this tells us here is that helium cannot get through the glass atoms anymore. So look what this thing does, which is insane, like literally insane. And this is why people love this stuff, because it is so interesting. So now this is a glazed glass. So guess what the liquid helium does? Because it lost atomic friction, that means there's no more friction that can hold it down. It actually climbs up the glass and literally starts leaking. Not leaking, but climbing the walls. So what we see here is that in this situation, liquid helium has the ability to defy gravity and climb up walls of the container. So what I mean by this silly question beforehand, when I was talking about this, I mean, why do you put water in a glass? Because you know it's going to stain here. That's not true for a superfluid. A superfluid has the ability to climb walls. So my point here, in summary here, helium-4 does not ever behave as a superfluid. But helium-3 does. The question is, why? It's the missing neutron. That one neutron really, really changes how liquid helium behaves, which is wild.